Async and await can make JavaScript easier to read, but they can also hide bugs that are hard to spot. In this video, we will go through 30 real async await mistakes beginners make, with broken code, clear explanations, and fixed versions. We start with the async basics. These mistakes look small, but they are the reason many beginner scripts print the wrong value or run in the wrong order. Imagine we need to fetch a user profile before printing the username. Here, the code calls fetchUser, but it does not wait for the result. Now we run the script and look at the output. Let's break down the result. FetchUser returns a promise immediately, and the real user object comes later. Since the promise itself has no name property, JavaScript prints undefined. Now we fix the mistake by awaiting fetchUser before reading the name. This tells JavaScript to pause this async function until the profile object is ready. Now we run it again and the terminal shows the real value. The best practice is to await a promise exactly where your code needs the real value. If the next line reads a property from the result, that is usually the place where await belongs. Here we are writing a tiny script that loads a config value before printing it. The problem is that this file uses await directly at the top level. Now we run it and JavaScript stops before the script can execute. Let's explain the syntax error. In many Node scripts, especially common JS files, await is only valid inside an async function. JavaScript rejects the file while parsing it. Now we fix it by creating an async main function. Inside main, await is allowed and the script still stays easy to read. Now we run it and the config value prints correctly. The best practice is to use top-level await only when your runtime and module format supported. For portable scripts, an async main function is simple and reliable. Here we are building a helper that calls an API and parses JSON. The helper uses await, but the function was declared like a normal function. Now we run the script and the parser rejects it. Let's look at the rule behind the error. Await is not just a normal keyword you can place anywhere. If a function contains await directly, that function must be declared async. Now we fix the helper by adding async before function getData. That makes await legal inside the function, and getData now returns a promise with the parsed object. Now we run it and see the parsed response. The best practice is simple. When a function directly uses await, declare that function as async. This keeps the async boundary clear for anyone reading the code. Imagine checkout must save an order before showing success. In this version, save order is called, but checkout does not wait for it. Now we run the script and watch the order of the logs. Let's break down the wrong order. Save order returns a promise, but checkout ignores that promise. So JavaScript continues to the success message before the save delay finishes. Now we fix the workflow by awaiting save order. The success message now means the save really finished. Now we run it again, and the output is in the correct order. The best practice is to skip await only when you truly want background work. If the next line depends on the async result, await the promise before moving on. Now we move from basic async flow to error handling. The key idea is that try-catch only helps when the rejected promise is connected to the try block. Imagine a payment API fails and we want to show a clean error message. This code has a try-catch, but charge card is called without await. Now we run it and the failure escapes the catch block. Let's explain why catch did not run. The try block only catches synchronous errors and rejected promises that are awaited inside it. Because charge card was not awaited, its rejection becomes detached. Now we fix the error handling by awaiting charge card inside the try block. If the promise rejects, JavaScript routes that rejection into the catch block. Now we run it and get the controlled error message. The best practice is to await promises inside try when you expect catch to handle failures. If you intentionally start background work, attach a catch handler to that promise separately. In this section, we will fix common async error handling mistakes. These examples show where errors should be caught, when to throw, and why silent failures are dangerous. Imagine this dashboard is loaded through a service function. The service can fail, but the caller just awaits it as if nothing can go wrong. Now we run the script and the app ends with an uncaught async error instead of a helpful message. Let's break down why this happens. The error is thrown inside load dashboard data, but it becomes a rejected promise. Since render dashboard does not handle that rejected promise, the failure escapes the async chain. Now we fix the caller because this layer knows what the user should see. We wrap the awaited service call in try catch and print a friendly fallback. When we run it again, the script no longer crashes. The best practice here is to catch errors at the layer that can make a real decision. A low-level service usually should not guess the UI fallback. The caller can decide whether to retry, show cache data, or display a clear message. In a login service, invalid credentials should stop the success path. This broken version returns an error object instead of throwing it. Now we run the script and the caller prints a misleading welcome message. Let's look at the problem. Await does not care that the value is an error object. If the promise resolves, the next line runs, so the caller treats the failed login like a successful user. Now we fix the service by throwing when the login is invalid. The caller uses try catch around the await, so the failure goes to the error branch. When we run it, we get a clear login failure. The best practice is simple. Return normal values only when the operation succeeds. For failed async work, throw an error and let the caller handle it. That keeps success and failure paths easy to read. Picture an importer that reads product records from a file. The file read fails, but the catch block is empty, so the failure disappears. Now we run it, and the terminal says the import finished with zero context. Let's unpack why this is dangerous. The original error had the exact reason, but the empty catch block threw that information away from the outside. This looks like a real import with zero records. Now we fix it by making the failure visible. The catch block logs the file error and returns an explicit failed result. When we run it, the terminal tells us both the cause and the final import status. The best practice is to make every caught error useful. Log it, rethrow it, or convert it into an explicit result the caller can understand. An empty catch should almost never survive code review. Now we move to async loops and collections. These mistakes happen when array helpers look synchronous, but the async work continues in the background. Here we need to send welcome emails to 3 users. The code looks reasonable, but for each does not wait for the async callback. Now we run it and the done message appears before the emails finish. Let's explain the ordering. For each calls the callback for each user and ignores the returned promises. That means the outer function reaches the done log while the email work is still pending. Now we fix it with a for of loop. This gives await a real place to pause before moving to the next user. When we run the script, every email is sent before the final done message. The best practice depends on the workflow. Use for of when order matters or when each operation should finish before the next one starts. Use Promise.all with map when independent async work can run in parallel. Here we load prices for 3 product IDs. Because the map callback is async, every item becomes a promise. Now we run it, and the terminal shows promise objects instead of numbers. Let's break down the result. Map is synchronous, so it only builds a new array. Since the callback is async, that new array contains promises waiting to resolve. Now we fix it by saving the promises and awaiting Promise.all. This waits until every price is resolved. When we run the script again, we get the actual numeric prices. The best practice is to pair async map with Promise.all when you need the resolved values. It keeps the work parallel and gives you one clean await point. Use this for independent requests like prices, users, or product details. Now we are moving into concurrency control. These mistakes are not syntax problems, but they can make real apps slow, unstable, or expensive when async work is not coordinated carefully. Imagine we are fetching product details for a catalog, and each request is independent. Here the code looks clean, but the await inside the loop starts the next request only after the previous one finishes. Now we run the script and the output shows the catalog data, but the total time is about the sum of all 3 delays. Let's break down why this happens. The second request does not even start until the first one is done, and the third request waits for the second one. That means the total time stacks up, even though these products do not depend on each other. Now we fix the mistake by creating all promises first and then awaiting them together. Promise.all keeps the result order, so the output is still predictable. Now we run it again, and the total time is closer to the longest single request. The best practice here is to run independent async operations in parallel with Promise.all. Use this when every request can start right away and you need all results before continuing. If one result depends on another, then sequential awaits may still be correct. Now picture an image upload job calling a third-party service. Promise.all starts every upload immediately. which sounds fast, but it can break when the service only allows a small number of active requests. Now we run this version and several uploads hit the fake rate limit. Let's look at the result. The first 2 uploads are allowed, but every extra upload starts while the service is already busy. The problem is not Promise.all itself. The problem is using it without a limit for a large workload. Now we fix it with a tiny concurrency pool. Only 2 worker loops run at the same time, so the active count stays under control while all images still get processed. Now we run it and every item completes. The best practice is to limit concurrency when calling external services or processing large workloads. Use a small pool when the service has rate limits, when jobs are heavy, or when the input array can grow large. This gives you parallelism without creating a traffic spike. Imagine a dashboard with optional widgets like weather, stocks, and calendar. In this broken version, one optional widget failure makes the whole Promise.all reject. Now we run it and only the first failure reaches the output. Let's unpack the behavior. Promise.all rejects as soon as one promise rejects, so the array of successful widget values is never returned. That is perfect for all or nothing tasks, but it is not ideal for optional dashboard sections. Now we switch to Promise.all settled because partial success is acceptable here. It gives us a result object for every widget, so we can show successful widgets and report the failed one. Now we run the fixed version and every outcome is visible. The best practice is to choose the promise helper based on the business rule. Use Promise.all when every operation must succeed together. Use Promise.all settled when you can keep useful partial results. Now we add a timeout around a slow network request. Promise erase returns when the timeout rejects first, but the original request has no cancellation path. Now we run it and notice the late completion log appears after the timeout. Let's explain the surprise. Promise erase only chooses the first settled promise. It does not cancel the others. The timeout changes what our async function sees, but the slow operation is still scheduled. Now we fix it with abort controller. When the timeout fires, it aborts the request, clears the timer, and runs cleanup, instead of letting the slow request finish later. Now we run the fixed version and the late completion is gone. The best practice is to pair timeouts with cancellation or cleanup. This matters for real. Fetch calls, file operations, queues, and anything that can keep consuming resources after the user no longer needs the result. Next, we look at resource management. Async code often opens connections, files, or locks, and cleanup has to be treated as real async work too. Imagine a database query fails and we still need to close the connection. In this broken version, close connection is async, but the finally block only starts it and immediately moves on. Now we run the script and the process says it is finished before the connection is closed. Let's break down the order. The finally block does run, but close connection returns a promise and nobody waits for it. So run query resolves the then callback prints process finished, and only later does the cleanup log appear. Now we fix the cleanup by awaiting it inside finally. This makes run query stay pending until the connection is actually closed. Now we run the fixed version and the cleanup happens before the process finished message. The best practice is to await asynchronous cleanup in finally blocks before the operation is allowed to finish. Use this for database connections, file handles, locks, browser contexts, and test cleanup. If cleanup matters, treat it like part of the operation. Now we move into resource management. These async bugs are easy to miss because the function may return successfully while still leaving something open. In real apps, this could be a locked file or a database connection. We open the file, read one row, and return early. When validation fails, now we run the script and check whether the resource was closed. Let's break down why this result is dangerous. Await paused the function while reading, but it did not protect the cleanup code. Once return runs, JavaScript leaves the function immediately and the close call is skipped. Now we fix the bug by wrapping the work in try. Finally, the return can still happen inside try, but finally runs before the async function resolves. Now we run it again, and the output shows the file being closed. The best practice here is simple. If an async function acquires something that must be released, put the release in finally. Use this for locks, file handles, browser streams, database transactions, and any cleanup that must happen on every path. For practice, change the fake row so validation passes. The important check is that close should still run, both when the import succeeds and when it returns early. Next, we look at the event loop. Await is powerful, but it does not freeze the whole JavaScript runtime. In a real app, this could be an API request while other UI or server work continues. Here we schedule a timer, then await a short delay. Now we run it and watch the order carefully. Let's explain the result. Await pauses only this async function, not the entire JavaScript runtime. While the promise is pending, the event loop can run other callbacks. The code does not need a mechanical fix as much as a mental model fix. We make the yield point explicit in the logs so the behavior is clear. Now the output describes what the runtime is doing. The best practice is to read await as yield until this promise settles. Apply this when debugging log order, loading states, server handlers, and anything that schedules callbacks around async work. For practice, add another timer with a 10 millisecond delay. Predict the order before running it, then compare your prediction with the terminal. This bug shows up when you debug app startup and the logs look backwards. We schedule a zero delay timer, a resolved promise, and an await continuation. Now we run it and compare the actual order with the naive expectation. Let's unpack the ordering. First, all synchronous code runs to completion. Then JavaScript drains the microtask queue, which includes promise, then callbacks, and await continuations, and only after that does the timer callback run. Now we fix the assumption by labeling the real queues in the code. The behavior is the same, but the comments and logs match how the event loop actually works. Now the terminal tells the correct story. The best practice is to remember this priority, promise continuations before timers. Use that rule when logs, state updates, or startup hooks seem to happen out of order. For practice, move the promise, then call below boot. Before running, predict which microtask is queued first and which log appears first. This is common when a service parses a huge payload before it awaits anything else. We schedule a progress timer, then run a big synchronous loop inside an async function. Now we run it and see that the timer is late. Let's explain the delay. The async keyword changes how promises are handled, but it does not move CPU work to another thread. A long loop still occupies the main JavaScript thread until it finishes. Now we fix the demo by splitting the heavy work into smaller chunks. After each chunk, we await a zero delay promise, so the event loop can process other callbacks. Now the progress timer gets a chance to run between chunks. The best practice is to treat expensive synchronous work as blocking, even inside async functions. For serious CPU work, chunk it, move it to a worker, or redesign the flow so the event loop can stay responsive. For practice, change the loop to 5 smaller chunks. Watch how the timer and chunk logs prove that the event loop gets more opportunities to run. The last lesson in this batch is about async function design. A wrapper function still needs to return the value it awaits. In a layered app, a service often wraps a repository call like this. The repository returns the name, but the service only awaits it and never passes the value back. Now we run the script and see what the caller receives. Let's break down the result. Await unwraps the repository promise inside getUsername, but that local result is ignored. Since the function reaches the end without return, JavaScript resolves it with undefined. Now we fix the wrapper by returning the repository promise. This is enough because async functions automatically adopt the returned promise. Now the caller receives the expected name. The best practice is to return from async wrappers unless the wrapper is intentionally fire and forget. Most service methods should return the promise or the resolved value so callers can use the result and handle failures. For practice, replace return fetch name from repository with return await fetch name from repository. The output stays the same, but this version can be useful when you need local try-catch behavior in the wrapper. In this section, we focus on async function design. Small choices in wrappers and promise flow can make code easier or harder to debug. Imagine this as a tiny API client method that only forwards data from another function. We write return await here, then run the script and see that the data prints correctly. The bug is not the value, the problem is that this wrapper suggests extra handling that does not exist. Let's break down why this matters. Since getUser does not catch, transform, or clean up anything, awaiting inside it does not make the result better. It only makes a pass-through function look like it has a reason to pause locally. Now we fix it by returning the promise directly. This keeps the wrapper honest. It simply hands back the fetch data promise. Now we run it again and get the same user with clearer intent. The best practice is to use return await when the function has a local reason to wait, like a try catch or finally block. If the function only passes the promise through, return the promise directly and keep the design simple. Here we are fetching a report and saving it to a database. The code uses await but then continues with a then chain and puts the fetch catch in the middle. Now we run it and the terminal only says something failed. Let's inspect the flow. The catch inside the chain only talks about fetch data, but save data is the function that actually fails because the final catch is generic. The terminal does not tell us which step broke. Now we fix it by separating the fetch step from the save step. Each operation gets its own error message, so the output tells us exactly what failed. Let's run this version and compare the result. The best practice here is to choose one readable style. For most beginner and intermediate code, clear await steps are easier to debug than an accidental mix of await. And then if you do use a promise chain, make the chain deliberate from start to finish. This section shows a common object setup problem. Some objects need async work before they are usable, but constructors are not the right place for await. Let's build a database client that needs to connect before use. A beginner might try to put async directly on the constructor and await the connection there. When we run it, JavaScript stops before the class can even be created. Let's explain the failure. A constructor is part of the new operation, and that operation expects an object right away. Since await pauses and returns through a promise, JavaScript does not allow async constructors. Now we fix it with a static async create method. The factory does the async connection first, then calls the normal constructor with a ready connection. Now we run it and the client is ready before we query. The best practice is to use an async factory when an object needs async setup. This makes the call site explicit because the user must await database client "create" before using the instance. Now we move into promise anti-patterns. These mistakes are more subtle because the code often looks asynchronous, but the error handling does not behave the way you expect. Here we are loading a token, and the code wraps the operation in new promise. The mistake is that the executor itself is async. When we run this, the catch block does not catch the token error, and the promise keeps waiting. Let's break down the bad behavior. The promise constructor only understands synchronous calls to resolve or reject from its executor. Once the executor is async, thrown errors belong to the executor's own promise, not the outer promise returned by load token. Now we fix it by removing the manual promise wrapper completely. An async function already returns a promise, and thrown errors become rejections. Now the catch block receives the real token error cleanly. The best practice is simple. Never use an async executor inside new promise. Use a plain async function for promise-based work, or use a non-async executor only when you're adapting a real callback API. Here, we start a report job and an email job before entering the controlled error handling block. The report job fails quickly, but the code waits before it attaches Promise.all inside try. Now we run it and see that the rejection is reported before the catch runs. Let's unpack the timing. A promise starts running as soon as it is created, not when you await it. If it can reject before a catch or Promise.all is attached, your intended error handling is too late. Now we fix the timing by creating the jobs inside the try block and immediately awaiting Promise.all. The promises can still run in parallel, but the rejection is connected to the catch right away. Now the terminal shows one predictable handled error. The best practice is to attach error handling as soon as a promise can reject. If you start work early for parallelism, connect it immediately to Promise.all, catch, or another controlled handler. In this section, we debug async code that fails far away from where the real business action started. In a real sync job, the database layer might fail several awaits below the job runner. We write the broken version first. The service simply awaits the database call and lets the raw error escape. Now we run it and the terminal only shows the database message. Let's break down why this output is weak. The message tells us what the database rejected, but not that we were syncing a customer record. In production logs, that missing context can be the difference between a quick fix and a long search. Now we fix the error path by catching the low-level failure and throwing a higher-level error with a cause. The new message says what business action failed, and the original error is still available for debugging. Now we run the fixed version and compare the output. The better pattern is to add domain context at the boundary where you understand the operation and keep the original error as the cause. Use this when async code moves through service layers, queues, jobs, or API handlers. You get readable logs without throwing away the root failure. This section covers async work that continues after the main request flow has already moved on. A common web pattern is to respond first, then start analytics in the background. Here the handler deliberately does not await the analytics call, but it also does not handle failure. Now we run it and see the rejection reported outside the normal flow. Let's unpack the bug. The request handler does not wait for analytics, so its try-catch would not protect that later failure. The promise is floating, and when it rejects, there is no local owner for the error. Now we keep the task detached, but we attach a logger directly to that promise. This keeps the request fast while still making the background failure explicit. Now we run the fixed code and the logger owns the error. The best practice here is simple. If you detach a promise on purpose, attach its error handler on purpose too. Use this for analytics, notifications, cleanup jobs, and any fire and forget work. A background task should never fail silently or become a global unhandled rejection. This section focuses on async flows that must stay correct when requests are slow, flaky, or obsolete. When an API is flaky, we usually retry with a short pause. In this broken version, the loop calls delay, but it forgets to await it, so the retry does not actually wait. Now we run it, and the attempts all happen at the same logical time. Let's look at the important line. Calling delay creates a promise, but without a wait, the loop does not pause for that promise. That means the retry storm can hit the same failing service instantly. Now we fix the loop by awaiting the delay and by keeping the last error for a real final failure. This version spaces the attempts and does not pretend that giving up is a successful result. Now we run it and the timestamps move forward between retries. The best practice is to make retry behavior visible and honest. Await the back-off delay, stop after a clear limit, and throw the last error if every attempt fails. Use this pattern around network calls, queue operations, and third-party APIs. This bug shows up when a user types a new search before the previous request returns. We start a slow search for Java, then a faster search for JavaScript. Now we run it and the old result overwrites the newer one. Let's reason through the timing. The JavaScript request is newer and finishes first, so it renders the right result. Then the older Java request finally resolves and writes state again, even though it is no longer the active search. Now we fix it with a request ID guard. Every search gets a token, and only the latest token is allowed to update the rendered result. Now we run it and the old result is ignored instead of becoming final. The best practice is to cancel obsolete async work when the API supports it, or ignore stale results with a token when cancellation is not available. Use this for search boxes, route changes, autocomplete, and live filters. The latest user intent should be the only result that updates the screen. In the final section, we look at async dependency design and how circular waits can freeze startup. Here, two startup services try to wait for each other before becoming ready. That dependency shape looks harmless in a larger codebase, but it creates a circular wait. Now we run it and startup never reaches either ready log. Let's explain the hang. Service A cannot resolve until service B resolves, and service B cannot resolve until service A resolves. Since neither service owns an independent first step, the system has no way to make progress. Now we fix the design by extracting the common startup requirement into one independent promise. Both services wait for shared initialization, but they do not wait for each other. Now we run it and startup completes in a clear order. The best practice is to make startup dependencies directional. Initialize shared prerequisites first, then start services that depend on them. If two services need each other to become ready, extract the shared part or introduce a clear coordinator. Now you have seen the most common async await bugs and how to fix them. If this helped you, like the video, subscribe to Dev Level Up, and comment what JavaScript topic or bug pattern you want explained next.